Good afternoon, everyone. I'm glad to see so many participants. And my name is Dangirutis Navikas. I'm professor in Kaunas University of Technology. And today I'm going to be the chairman of this session on electronics. We have 6 presentations. And of course, you know, the time of each presentation is limited to 15 minutes, including discussion and questions. So try to be in time on your presentation. If we have time left after all presentations, we can make some discussion or answer additional questions if there will be. Audience can ask the questions on the Zoom chat, or those who are watching on the YouTube can write also the questions on YouTube, and we'll try to transfer those questions to presenter. And now we will start from presentation from Czech Republic. The presenter is Jaromir Konecny. And the title of presentation is Optimizing of Pure Learning Day-Night Energy Strategy for Solar Harvesting Environmental Wireless Sensor Networks Nodes. So the stage is yours, please.
Everyone. I'm sorry, I click on the close window, so I don't get the last 5 sentences. Okay, I try to start the video right now. So, and I'm gonna share the presentation, right? So the presentation is seen or not?
You should switch to other view. We see, but it's in. You should change the view. Present.
Yeah. I don't know what happened because I have only one mirror screen, and if I start.
Yeah, but it's on the top of the screen. There is selection for those screens.
Okay.
When you start, now I cannot understand Czech, I think, but it's наставни изображения on the top. Here you should change, and choose the.
So
now
it's okay right now.
Yeah.
Okay. So hello everyone. Once again, good afternoon from sunny Czech Republic. So I would like to present a paper optimizing of Q-learning day-night energy strategy for solar harvesting environment wireless sensor network nodes. So my name is Jaromir Konecny, and this paper is written with Michal Prauzek. Okay, so something for introduction. So in this paper, we are presenting the follow-up research based on the previous paper that focus to design of a hybrid energy management strategy with Q-learning control during daylight and a linear discharging process at night. We are presenting a method to optimize Q-learning parameters to achieve the best and stable performance results. Okay, so let's switch to environmental wireless sensor node and model and data. We are using an energy harvesting EVSN node model. It contains ARM Cortex microcontroller, solar power charging module, energy storage represented by two serial connected supercapacitor, and the data storage module, and also a low power wireless interface. So basically, you can see the picture of a real hardware, and we are simulating those hardware. We are using 5 years data from Fairview Agriculture Monitoring Station located in Canada, and we are using data set with solar radiance measured by 5-minute interval continuously from 2008 to 2012. We are using this time interval due to easy quantitative comparison to previous studies. Now something about the Q-learning method. The Q-learning belongs to the group of reinforcement learning methods. The algorithm is suitable candidate which can control an embedded system represented by an VSN node. And it is not very extensive in terms of computer performance. This approach uses properly defined policy, and it could be used to perform an optimal EFSN node management of data collection and wireless transmission. I can say the Q-learning is one of less candidate, because a lot of machine learning methods are dedicated for data processing, and we need to some agent which can plan an actions and control the behavior of some wireless node. The implementation of Q-learning method use Q-table, and basically that is an array stored in memory, and each column represents quantitative values of the actions. The basic idea is to estimate the future reward represented by Q table for performed action A in the state S, and at the same time follow the optimal internal policy. So basically we have some Q table that represents the best action for particular state S. So we have some set of states and set of actions, and we are searching the best action for each state, and the Q table is continuously modified by the reward obtained from the agent. So Q represents estimate of the reward value for the currently performed action A, and there are two coefficients. The first is alpha, that is a learning rate. If alpha is 0, so algorithm use only knowledge gained from the previous steps, and if the algorithm has alpha 1, uses only new knowledge. Basically, we are using something in the middle. The R represents learning feedback from a current reward, and the gamma parameter is the discount factor that determines whether the current reward or cumulative reward is preferred. So basically, if gamma is close to 0, so the algorithm preferred instant reward, and if gamma is close to 1, it prefer the cumulative reward. So we are presenting an experiment for day and night algorithm. The key is the day algorithm. So the algorithm for daylight mode is based on the intensity of sunlight over the past 30 minutes. This information can be obtained from the difference between the amount of energy in the supercapacitor, represented by state of an energy storage, and the amount of energy consumed by the EVS node activity. The consumed energy can be also calculated as the energy required for one action times the number of action plus the static consumption of the EVS node. Here we can see the state table. So basically the state ranges in the solar ratio parameter provide height resolution for very low solar irradiation. So if we have only few sunshine, the systems is in states 1, 2, or 3. For medium resolution, so if we have more sun, the system is in a state 3 to 6, and for high sunlight conditions, so let's say ideal sunlight condition, this we have states 7 to 10, and the state 11 is designed for ideal sunshine condition more than 60% of maximum solar irradiation. So we need to expect what is the maximum solar radiation for our geographic location, and we calculate it in percentage. The daily goal in this experiment is very closely related to reward policy. The reward policy consists with 3 basic parts. The first part, rewards, is depend for performing action. The reward strategy considers the need to collect data from the environment by the EVS node, and the agent receive the highest reward for the shortest operational period. We can say that shortest period means the highest consumption. So we need to find some trade-off between the energy that we can obtain from the environment and the duty cycle, so measuring period. So for action 1 minute, we get a reward 1, and for the interval 30 minutes, we obtain a smaller reward. The second part represents the fulfillment of the charging target. This reaches the maximum value of 1 when the agent fulfills the selected target. When the agent starts overcharging, this reward decreases. The reward value on recharging is limited when recharging by more than 90% of the charging target. In this case, the reward is set to 0.1. So basically, it's about the charging target, the second part of the reward, and we need to obtain an energy during the day for night, because at the night we have no sunshine, and we need to collect some energy in order to measuring in the night. And last part of the reward is a penalty for lack of energy in the EVS node. Basically, when the node has no energy and fails, so the microcontroller down and everything down, the algorithm obtain a penalty, and the reward is set to minus 0.5. So basically, this is a penalty for bad action. In the night, as I said, there is no solar energy available. So the policy of control algorithm is set differently than during the daylight period. The device is discharged linearly depending on the current state of the energy storage, then remaining length of the night and estimated energy required for one operational cycle. So basically, at the end of the day, we have some specific amount of energy. We know how the night is long, and we can set the period for measuring, and for the start of the day, we have some small energy for the day start, around 20%. So let's switch to results. Here you can see the 3D graph of total count selected actions during the 30 days in the summer and winter. So the left side is the summer, and the right side is the winter. Maybe I hope my mouse is seen. So the colors means the period. So we try to measure in a high lowest period. So that means higher frequency. So 1 minute is the lowest period. So we can see that in the summer we can measure in 1 minute interval, and also during the short night, because in Canada it's a very short night in the summer. And in the right side, we can see that in the winter there is no opportunity to measure so fast. So the algorithms choose another states, and during the very long night and very short day, the measuring cycle is around 10 to 30 minutes. Here you can see the typical trend of the summer period and the winter period. The red curve represent state of the energy storage. So basically, the amount of energy in supercapacitor. During the night is the energy goes down, and during the day and there is a very short time to obtain a maximum, and this getting is an overcharge, so this is an unused energy. Also, here you can see the actions chosen by an algorithm, and here you can see the harvested energy. So basically, it reflects solar irradiance. In the winter is a totally different situation. So I choose some days that was lack of an energy. So you can see that here the algorithm can obtain some energy, but here almost nothing. And this line at the bottom means a failure because there is no energy. In this paper, we also try to find an optimal settings of alpha and gamma parameters. Note this reminder that alpha 0 means slower learning, alpha 1 fast learning, gamma 0 instant reward, and gamma 1 cumulative reward. Researching about 3 parameters, so we try to maximize thousands of cycles, so maximize number of measuring cycles. We try to minimize failure count, and we try to minimize overcharging count.
Sorry, Jaromir, the time is.
Oh, I'm sorry.
You can conclude, okay?
I'm sorry. So here you can see only a combination of the 3 graphs. Basically, the best area is near gamma 0 and alpha also 0. So if no time is, so conclusion you can read in this paper, and I'm so sorry for the delay.
Okay, no problem.
Thank you for your attention.
Thank you. Do we have any questions? I have one question. How the day and night period is selected? Is it real-time clock or in the real application, I mean? Yeah. In the simulation, we are using NOAA calculation. So it's some sort of a lot of sinus cosinus functions, and you can calculate when on a particular location the sun for each day starts and set, and when is the sunrise and when is the sunset. And basically for each location we can produce the lookup table, so the implementation in microcontroller will be very easy. But microcontroller must have a real-time clock. Yes, some microcontrollers can have real time. Yeah, must have real-time clock. Yeah, but and also there could be some problems with synchronization of time. Yes, because if you put microcontroller for 1 year, yeah, without any synchronization, it could the time can be shifted for half an hour or maybe more. Yeah, maybe this model is based on a little bit older wireless technology, but we are looking for LoRaWAN, and there is also some possibility to transmit data, and receive data and receive some synchronization and some. Okay, thank you. If there are no more questions, we can proceed. Thank you, Jaromir. Now we will have presentation from Bulgaria, and the presenter is Ivailo Pandiev, and the topic of presentation: dynamic FPAA-based mixed signal processing circuit for thin film cadmium tellurate lead-free perovskite photodetectors. Please.
Okay, thank you very much. Is it?
We can hear you. We can't hear you.
Something went wrong.
Yeah. But it's showing that he is connected.
Yes. Maybe it is better to go with next presentation.
Yeah, maybe. And okay. And then we can switch to this topic later. Okay. And then we will have a presentation from Thailand. Pwint Y, and the topic is electronically and orthogonally tunable SITO voltage mode multifunctional Biquad filter using LTE-1228. Oh, Ivailo now is connected, but maybe put your mic on, switch your mic.
Yes, I am.
The internet was lost. The internet connection. I'm ready.
Okay, if you are ready, then we
Yes.
can continue from you.
Yes, I think.
Sorry, me. We will. You will be the next. Again, the same problem. I don't know what's happening.
Is it possible to represent or other colleague will be?
No, you can represent, but you must share your screen and then.
Okay. I don't understand. Okay. Is it good to
and switch it to full screen mode. Okay.
And now?
Okay.
Okay, thank you very much. And excuse me for the problem, but the internet was lost. Okay, dear colleagues, my name is Ivailo Pandiev. I'm from the Technical University of Sofia, and now I would like to present to your attention a paper entitled Dynamic FPAA-based Mixed Signal Processing Circuit for Thin Film Cadmium Telluride Lead-Free Perovskite Photodetectors. The authors of this paper is Ivailo Pandiev and Mariya Aleksandrova from Department of Electronics and Department of Microelectronics, respectively. The content of this paper include introduction, motivation, and aim of the work. The second one is fabrication of thin film cadmium telluride lead-free perovskite photodetectors. The third one is about design and implementation of FPAA-based processing circuit. And here we have results and discussions. And the last one is conclusions. The well-studied cadmium telluride-based solar cell inhibit long-term stability of the electrical characteristic due to their photochemical stability. Unfortunately, the fumes from cadmium telluride usually consist of pinhole, and for their reason, their thickness cannot be decreased to smaller than 4 up to 5 micrometers. In the last few years, growth of interest in organic perovskite-based solar cells have been observed due to their combination of the high efficiency and easy preparation. However, their stability is still an issue, especially as related to the novel lead-free perovskites. What is the aim of our work? In this paper, it's proposed a novel design of photoelectric element implementing lead-free perovskite material in combination with thin cadmium telluride coating with an application in thin film photodetectors. There are some benefits that you can see on the slide with 3 benefits. And of course, we have some problems. The problems that have to be overcome are two basic. The first one is lower current generated at the same time, at the same light intensity as compared with the thick non-perovskite material structures. And the second one problem is about the lower value of the internal resistance. This problem and these specific conditions have to be decided during the design of suitable processing circuits. One possible way to realize the processing circuit is by using integrated field programmable analog array with abbreviation FPAA based circuit. And they're suitable due to the first one, possibility for dynamic variation of the circuit parameter following the variation of the input, the parameters of the input signal, such as amplitude and noise level. Also, frequency response of the high frequency components as parasitic elements in the signal. And the second one, usage of reconfigurable integrated circuits allow design of fully integrated device without any external discrete passive components. On the right side of this slide are presented the internal structure of the simplified FPAA circuit. The basic one element is configurable analog block, and each of these blocks can be configured as amplifier, active filter, comparator, summer, integrator, analog to digital converter, etc. Many of the small signal analog circuits can be realized by using configurable analog blocks. Also, we have interconnection channels that connects the configurable analog blocks each other. And also these channels are using to connect the configurable analog blocks with input and output ports. The programming of this type of monolithic integrated circuit is performed by external digital circuit or by using microcontroller. Also in this configuration, in many cases are used personal computer to create the programming code, or by using a specialized program with graphical user interface. The analysis of the literature shows that it's in the first time of investigation, FPA-based processing circuit integrated with cadmium telluride lead-free perovskite photodetector. In this slide are presented some things about fabrication of this type of photodetectors. On the left side are presented the structure of this device, electronic device, and here is presented the different layers. On the right side are presented some things about it and details about the different layers. And below is presented a small picture that represents the experimental setup for measurement of the optoelectronic characteristics of this device. What about of the design of FPA processing circuit? The input signal is photocurrent, because this electronic component generating photocurrent with specific internal resistance. As an input stage is used transimpedance amplifier or current controlled voltage source, such as operational amplifier with resistors that are connected between inverting input and output. In this slide is presented the basic parameters at low frequencies and also the parameters pole frequency and zero frequency at higher frequency. To stabilize this electronic circuit is necessary to connect additionally feedback capacitor in parallel of the feedback resistor, and as a result is obtained high current, high cutoff frequency or corner frequency that is related basically with operating bandwidth. And below are presented frequency responses for this electronic circuit. After obtaining a voltage proportional to a photocurrent, the output of the amplifier is often connected to low-pass filter to eliminate high-frequency parasitic components. And then it's transferred to signal sampling circuits. Within the realization with FPAA electronic circuit is used analog to digital, can be realized analog to digital converter or voltage to frequency converter. What about of the analog to digital converters? There are two types that can be realized with FPAA integrated circuit. The first one is parallel two-step data converter, and the second one is successive approximation data converter. For the parallel data converters, we have to use many of the resources of the FPAA, and as a result, it's realized successive approximation data converter that use resources only of the one of the configurable analog block. Also, the output signal that are proportional to the input voltage is obtained in series mode, and we are using only 3 wires or 3 pins from which we can obtain a synchronization signal, data signal, and master clock frequency. These signals are compatible with standard SPI interface that are using for connection between integrated circuits. In some practical applications, the signal process, the successive approximation data converter is not suitable because the resolution is up to 9 bits. As a result, we are realizing the voltage to frequency converter or pulse-wide modulator. As you can see in this slide, here is presented the circuit diagram and the signals from the input and output waveforms. As you can see, the output voltage that are produced from the transimpedance amplifier through low-pass filter is applied to the non-inverting input of the analog comparator, and to the inverting input is applied the sawtooth signal that are produced from the internal quartz stabilized oscillator. And also here is presented some timing diagrams, and of course the output signal where the period of the signal is constant, but the pulse wide is variable according to the comparison between the two input signals. Also in this slide are presented some analytical expressions about the input signals here and about the output signals that can be used to obtain the design methodology to obtain the values of the various parameters of the different blocks according to the parameters of the input signal. Here is presented the implementation of the FPAA processing circuit. As you can see, here is presented the external view of the FPAA configuration in Anadin Designer program. As you can see, this program we have graphical user interface, and various blocks are presented as symbols. And this graphical user interface is very close to the graphical user interface of the schematic capture from ORCAD PSpice, for example. Also, we have input and output ports where we can to obtain the input and output signals. And in the right side of the window, we can to obtain the information about the used resources and also the power consumption. In this slide are presented the parameters of the configurable analog blocks and their starting values that can be changed during the variation of the input signal, and below are presented the timing diagram of the output signals from analog to digital converter. And the last one is about the input and output stage of the processing circuit. The input stage is transimpedance amplifier, where the transimpedance can be changed during the change of the master clock frequency of the integrated circuit with suitable dividers, frequency dividers. And also, we have to see that all signals that are outside and inside of this electronic, in this integrated circuit, are in differential form. As a result, the noise level are with lower value, because this type of electronic circuits used SC technology, switch capacitor based technology. The output stage of this processing circuit is realized by differential amplifier, where the output signal is proportional to the single-ended and is referred to the analog ground. As you can see, here is presented the transfer function for the low pass frequency, for the low frequencies, and also some parameters about high frequencies also are given the rise time that can be obtained. Figure 8 represents electronic response of the produced photodetectors. As you can see in number A, is presented different light intensities of white light. Number B representing different light colors at the constant light intensity equal to 400 candela per square meters. And in number C are presented the linearity of the photodetector, where we can see that the non-linearity is not higher than 0.6%. In figure 8 is represented response speed of the produced photodetector at white light with the maximum intensity equal to 400 candela per square meters. In number A are presented general view of the pulses at light to dark transition and vice versa. And in number B and C are represented rise time and fall time during the transition between the two stable state operation. As you can see, the rise time and fall time is not higher than 30 milliseconds. Here is presented external setup of the prototype of the mixed signal processing circuit. As you can see, here is the photodetectors, here is the PCB board where is realized the differential amplifier and also the FPAA electronic circuit, and some interface integrated circuit. Also, we have a personal computer that we are using to program the FPAA electronic circuit and to obtain the value of the output voltage that is produced from the transimpedance amplifier. Also, the signal in graphical form can be illustrated by using two-channel digital oscilloscope. Below is presented some only two output waveforms on light with intensity around 450 candela per square meters, and the second one is on dark. As you can see, the light of the pulse light is very small, and it depends on the offset voltage of the electronic circuit. As a conclusion, in summary, a lead-free perovskite material was introduced to cadmium telluride based photoelectric thin film device for decreasing the absorbing layer thickness by keeping at the same time the performance parameter to levels competitive to the state-of-the-art detectors that use advanced photoelectric materials. The future work of the authors are related to investigation of long-term stability at outdoor conditions and to decrease of the sensitivity area by keeping the values of the performance parameter in the same range. And the last one is related to the acknowledgement. The study was financially supported by Bulgarian National Science Fund under the program for bilateral cooperation between Bulgaria and India that started in 2019. And as a last one, I have to say that full details about this work is published in scientific journal Electronically, Electrotechnica, which is open access on volume 27, number 2 from this year. Thank you very much for your attention.
Thank you. So, does anybody has any question? I would like to ask, in what kind of application these kind of detectors can be used, applied? For what applications?
Maybe this question can be answered. My colleague Mariya Aleksandrova, she is also in online.
Okay.
Because she is the central person that produced this type of photodetectors.
Hello. Well, this is actually a conventional photocell that could be used like any other photodetector for, let's say, darkening conditions and detection motion or moving of objects when the illumination of the ambient is not too high or not too low. I mean, there is a sensitivity even at low illumination, which makes the benefits of this photodetector, making it at the same time thin film photodetector, not like the conventional bulk ones.
Okay, thank you. More questions? No, we are in a rush, so thank you, Ivailo. And I already introduced May. Yes.
Thank you very much. Yes, I will stop the share.
Yes, stop the share. And May I please you share your screen and start the presentation, okay?
Okay. I would like to present the SITO, Electronically and Orthogonally Tunable SITO for the multifunction Biquad data using FPAA. My name is Michal. I am PhD student in Michal in Electrical Engineering, the Faculty of Industrial Education, Chemical Institute of Technology, Lithuania. Here is my outline of my presentation. I would like to present the background of my research. At this analog data using electronically tunable building blocks has mainly focused the research topic area due to its advantages, such as it gives a better adjustment than varying the specific element value. Second, it is significant building block of analog signal processing, automatic control, and implementation systems such as touchstone telephone systems, three-way crossover network, digital derivation, fixed lawless circuit. Next slide, I would like to present the problem. The disconnected or active building block with different diode commercially IC, such as it cannot provide the separate function at the same time. Second is it cannot provide either electronic or independent candidate. That is, it cannot have possess high input impedance or low output impedance. It is, it cannot use grounded capacitor. Sometimes it requires additional circuits, such as inverting input or dividing amplifier. This is our research purpose. First is to investigate the effectiveness of proposed circuits. Second is to compare the circuit performance of the proposed circuits with previous work. This is my methodology. There has a lot of disadvantages, such as all grounded capacitor doesn't use. Second is providing separate function at the same time. Third is normal low output impedance doesn't have. Fourth is electronic candidate doesn't provide. phase independent tunable of center frequency and quality factor. This reference citation has voltage differential different amplifier and voltage differential differential input buffer amplifier are constructed from two commercially viable IC, LM13700 and 8800. Voltage differential buffer amplifier is constructed from two commercially viable IC, CA380 and F356. Four terminal floating Miller is constructed from two commercially viable IC, 8844. This is my research methodology. This figure shows the synthesis of multifunction data. It consists of 5 building blocks, 10 voltage sending circuits, 2 losses indicator, voltage gain amplifier. It has single input voltage and 3 output voltage, VDD, VAC, VLD. A and B is assigned the time constant of 2 losses indicator. K is the voltage gain amplifier. The 3 voltage transfer function, VLD, VAC, VDD is obtained in equation 1. From equation 1, the center frequency and quality factor is like this. From equation 2, the quality factor is orthogonally controlled by varying the value of voltage gain amplifier. Moreover, center frequency is linearly adjusted by changing time constant volt indicator. Here is the proposed multifunction data. This figure consists of 3 LC1228, 4 resistor, and 2 grounded capacitor. First losser indicator is constructed from first LC1228 and C1. The second losser indicator is constructed from second LC1228 and C2. The voltage gain amplifier is constructed from first LC1228 and resistor R4. The single input VA is applied to semi-or input voltage signal. The semi-or output voltage signal is type VAC high pass now. The output of first losser indicator is VLD. The output of gain amplifier is VDD. It has the VAC and VDD node provide low output impedance, so it can be directly connected to other circuits without using additional buffer. Here is the low pass function, high pass function, reverse function, and this center frequency and quality factor is like this. In this equation, the quality factor is orthogonally controlled by varying the ID3. The moreover, center frequency is electronically controlled by varying ID1 and ID2. In this equation, sanity bias is equal to a phi value and capacitor value is equal to same value. So the equation obtained is 5. In this equation, quality factor is independently controlled by varying ID3. The center frequency is linearly and electronically controlled by varying ID. There is a parasitic effect of LC1228 from, according to data sheet of LC1228, to set higher operational frequency and to reduce time resistance effect. Feeder resistor R1 should be low. If operational frequency bandwidth is less than 10 MHz, this parasitic effect are considered and other parasitic effect is ignored. Moreover, if operational frequency bandwidth is less than this, the effect of CdTe is also ignored. So the low pass function, high pass function in equation 6. And then the center frequency and quality factor obtained in equation 8. From equation 6 to 8, the parasitic effect of LC1228 affect the performance of proposed circuits, which are operating frequency, center frequency, and quality factor, and gain, voltage gain. Here's the simulation result. The supply voltage are plus or minus 5 volts. Its identifier is 100 microampere. All resistance are 1 kilo ohm. All two grounded capacitor is 2.7 nanofarad. Analyzing equation 5, center frequency and quality factor is like this. This figure shows the magnitude response of dB, LB, HP versus frequency. From this simulation, center frequency and quality factor is like this. So we can calculate percent deviation of quality factor is 1.27% and center frequency is 1.6%. And this figure shows that the bandwidth of low value of R1 is higher than the bandwidth at high value of R1. Because the R1 are 0.2 kilohertz, the operational bandwidth is higher. 5 kilo ohm hertz, operational bandwidth is lower. In our design, to achieve higher operational frequency, these feeder resistors are chosen as 1 kilo ohm. This figure shows the transient response of PV theta function where input or sinusoidal input is 50 millivolts to the linear operating region, and standard frequency is 100 kilohertz. And this figure shows the PD response for 3 different ID3 values. For ID3, 123.5 microampere, quality factor is 1.4. For ID3, 185.5 microampere, quality factor is 0.9. For ID3, 371 microampere, quality factor is 0.5. That standard frequency is constant 100 kilohertz. So this figure shows that the two can be independently controlled by adjusting ID3. And also this figure shows the standard frequency constant, the quality factor is changes for 3 different values. R4 1 kilo ohm, quality factor is 1.6. R4 2 kilo ohm, quality factor is 0.9. R4 3 kilo ohm, quality factor is 0.6. So it can be independently controlled by varying the value of R4 without affecting standard frequency. And also this figure shows the standard frequency can be electronically tuned by varying the ID1, ID2 equal to ID. In particular, this decimal of ID1, ID2 are easily implemented by using microcontroller or microcomputer. This figure shows the DC buses value input MPG. The input linear rate is 50 millivolts because internet construction of M3128 is BGD-ODA. This figure shows the PAC is 1%, lower than 1% when applying voltage 50 millivolts. And this figure shows the multi-tone test and best figure. For 3 different frequencies, 10 kilohertz, standard frequency 100 kilohertz, high frequency 1 megahertz. So attenuation between 10 kilohertz and standard frequency is minus 25.52 dB. And also standard frequency and high frequency 1 megahertz attenuation is minus 5.82 dB. And also this the experimental result. This experimental result component value are same as simulation result. So this figure shows the experimental and theoretical value XPMBDD versus frequency. This simulation has standard frequency is 100 kilohertz. Analyzing equation 5, standard frequency is calculated value is 102.09, 2 is there 1.732. This figure has applied sinusoidal input voltage is 50 millivolts P2P because to see the linear rate of LT1228. And also this figure shows transient response of PP figure for 3 different frequencies. First is 50 kilohertz low frequency, second is standard frequency 100 kilohertz, third is high frequency 500 kilohertz. From this figure, low frequency 50 kilohertz, high frequency 500 kilohertz, output signal is attenuated. That the standard frequency 100 kilohertz, output and input are same value. This figure shows the standard frequency. Without affecting standard frequency, 2 is linearly and electronically tuned by ID3. ID3 assigned to 123.5 microampere, 185.5 microampere, 371 microampere. They have the standard frequency doesn't change, has 2 values stay. And also this figure shows that there are 3 different values, 1 kilo ohm, 2 kilo ohm, 3 kilo ohm. The standard frequency is constant 100 kilohertz. The 2 value is changes. And also this figure shows the standard frequency changes, the 2 value is constant 1.6. For ID 123.5 microampere, standard frequency is located 125.311. For ID 185.5 microampere, standard frequency is situated 17.353 microampere. ID 371 microampere, standard frequency is located 374.25 kilohertz. So the standard frequency can be controlled quickly constant to by simultaneously varying ID1 ID2 value. So there's a comparison and discussion. In my comparison today, there has a lot of configuration. Some are single input, multiple output, other are multiple input, multiple output, and some are multiple input, single output. Some reference constructed from 5LT1228. Some are constructed from differential commercially viable ICs. Some reference doesn't use grounded capacitor. Some reference doesn't provide several functions at the same time, but in my proposal, only provide MBHPDD response, but it is suitable to use in three-way crossover network. In reference number, some reference number, low output impedance does not provide. So it requires buffer amplifier to connect to other circuits. And some has center frequency and quality factor doesn't provide electronic controllability. And some are independent candidates doesn't provide. This is the conclusion slide. It has the 3 super LT1228, 2 grounded capacitor, 4 resistor, and it can provide MBHPDD response, which is suitable to use in three-way crossover network. The HPDD response is low output impedance, so it cannot require additional buffer to connect to other circuits. And this provides center frequency and quality factor is independently electronically controlled. Moreover, the quality factor can be controlled by ordering set LT1228 without affecting the center frequency. The simulation and experimental results are achieved with theoretical analysis. The operational from simulation and experimental results, the operational frequency rate is lower than 10 MHz, and then so the harmonic distortion is lower 1% when applying amplitude lower than 50 millivolts. Thank you for your attention. Any questions?
Thank you. So any questions from the audience?
Maybe I have one.
Okay.
Okay, so how would you suggest to reduce parasitic capacitance at the high frequencies in your proposed filter?
Yes, in my experiment, simulation result, the LT1228 capacitor effect at high frequency, so the theoretical experiment is slightly deviate. Please ask me, okay?
The sound quality is terrible. I don't know who understands. Okay, I think we don't have more questions. Thank you. And we continue to the next presentation.
Yes.
Okay, thank you. May. You shouldn't share your screen.
Yes.
Okay, and then now we have a presenter from Turkey, Hasan Sisekli, and the topic is a MOS-C based electronically tunable current voltage mode third order quadrature oscillator and B-quadratic filter realization. Please.
Okay. Is everything working?
Yes, perfect.
Okay. Hello to everyone. It is a great pleasure for me to attend this conference and give you a presentation about our paper, which is entitled MOS-C based electronically tunable current voltage mode third order quadrature oscillator and biquadratic filter realization. My name is Hasan Sisekli. I am from Mustafa Kemal University, Turkey. And my colleague Ahmet Gökçen is from Iskenderun Technical University. Let me start by giving the outlines of my presentation. In the introduction section, I will explain the objective and the prominent features of our study. Then I will give the circuit description of the active element which we used in this study. Its name is second generation current conveyor and multi-output second generation current conveyor. In the third section, I will introduce the proposed circuit topology. Then realization of third order quadrature oscillator will be given. And following section is non-ideal analysis. After explaining the simulation results, I will give the outcome of this study in conclusion section. Now let me give some information about the basic concepts of the sinusoidal oscillators. The quadrature oscillators produce two sinusoid signals with 90-degree phase difference in periodic form, and they are commonly used in signal processing applications, telecommunication, measurement, instrumentation, and industrial control systems. And they play an essential role in phase modulators, quadrature mixers, and signal generators. It is a fact that higher order circuits that exhibit better frequency response, work more accurate, and achieve better distortion performance than the lower order circuits. Therefore, realization of third order oscillator has been received considerable attention in recent years. Design of quadrature oscillator using passive components which are all grounded has always been popular due to its suitability for integration technique and occupying less chip space. Furthermore, a topology which provides both current mode and voltage mode output is a desired feature for dual mode operations. Main features of the proposed oscillator are use of CMOS-based active resistors, which makes the circuit compatible with monolithic integration. And oscillation condition and frequency of oscillation can be controlled independently and also electronically. Availability of both voltage mode and current mode quadrature outputs in the same topology. And capacitors are all grounded, which is a desired feature for integration and beneficial in parasitic capacitance absorption and suitability for low voltage applications. Now let me give you the circuit description of the active element, which is named second generation current conveyor. You see two figures. The top one is about the second generation current conveyor. It has three terminals, which are represented by X, Y, and Z. Operation of the active element can be briefly described as the input voltage of the Y terminal is conveyed to X terminal, and X terminal current is conveyed to Z output terminal. And at the bottom, you see the figure of multi-output second generation current conveyor. The only difference is the number of outputs. We can add extra output by connecting additional output stage to the second generation current conveyor circuit. In equation 1, you see the definition equation of multi-output second generation current conveyor. The input current of Y terminal is equal to 0, and the X terminal voltage is equal to Y terminal voltage. And in the third and following rows, you see the relation between the output currents. Z output current is equal to X terminal current by same sign or the opposite sign. If the sign is positive, it means that X terminal current and Z terminal currents are in same direction. And if the sign is negative, it means that the input and output currents are in opposite direction. Terminal Y exhibits infinite input impedance. That is assumed that no current flows through Y terminal, and terminal Z has very high impedance. It is infinite in the ideal case. In this figure, you see the proposed circuit topology of the biquadratic filter. We used two second generation current conveyor, and in the equation number 2, we show the transfer function, voltage transfer function of the filter. From this equation, we can synthesize three filter types, which are called low pass, high pass, and band pass filters. And the combinations of 4 admittance seen in the table, and also the transfer functions and angular frequency formulas are located in the table. The quality factor formula is given in equation 3 at the bottom. And sensitivity analysis has been done by showing you the equations from number from 4 to 9. This equations shows that the passive component sensitivities are less than unity. And now you see the 3 circuits of the filters which are implemented, MOS-C implementation of the synthesized filters. The figure A shows the low pass filters, and B is high pass filter, and C is band pass filter. As you see, the resistors, the passive resistors are replaced by their MOSFET conjugates, and all the capacitors are grounded. Now let me give you some basic concepts of the third order oscillator. In this page, you see the schematic diagram of the third order quadrature oscillator. In this study, we used the principle of second order low pass filter cascade connection by inverting integrator and then forming a feedback connection to obtain a unity gain. And the system loop gain is equal to AS, BS. AS is the gain of the low pass filter, and BS is the gain of the inverting integrator. The Barkhausen criterion tells that if the gain of the low pass filter and the inverting integrator multiplication is equal to unity, the circuit will produce 2 quadrature signals at a single frequency. It is shown at number 10 equation. Using this schematic diagram, we constitute the third order oscillator, as you see in this figure. The bottom 2 active elements, number 1 and number 2, are low pass filter, and then we connected the output by the third active element, multi-output current conveyor, as a feedback connection. With this configuration, we obtain 2 voltage outputs and 2 current outputs simultaneously. And in this figure, we show the MOS-C implementation of the third order oscillator. The resistors are replaced by MOSFET conjugates. All of the passive elements are grounded. And as seen from this figure, the oscillation frequency can be electronically tuned by gate voltage of the MOSFETs. Now let's do the circuit analysis of the oscillator. In equation 11, you see the gain of the low pass filter in multiplication by gain of the integrator is equal to unity, and the characteristic equation is shown in equation 12. Frequency of oscillation is calculated as in the equation number 13, and the oscillation condition is shown in equation 14. Into equation from 13 and 14, we can say that R1, R3, and R5 and C5 can control the oscillation condition without interacting the oscillation frequency. And likewise, the oscillation frequency can tune by R2, R4, and C4. The circuit analysis yields us the current transfer function from IO2 to IO1 as given in equation 15. And in sinusoidal state, it is written in equation 16. This equation shows that there is a 90-degree phase difference between the 2 quadrature outputs. If we calculate the voltage transfer function similarly, we obtain the equation numbered in 17, and in sinusoidal case, it is shown in 18. And this equation shows that the phase difference between two voltage outputs is equal to 90 degrees. Frequency sensitivity against passive components variations is calculated as in equation 19, and it shows that the passive component sensitivities are all lesser than unity. Now let's discuss the non-ideal analysis of the active element. In equation 20, you see the definition equation in non-ideal case. And in ideal case, we assume that current transfer ratio is equal to 1 and voltage transfer ratio is equal to 1. But in non-ideal case, current tracking error and voltage tracking error parameters must be taken into consideration. So in analysis in non-ideal analysis, we will use the equation numbered 20. If we calculate the voltage transfer for non-ideal case, we obtain the equation given in 21. And the equation that satisfies the oscillation condition, it can be rearranged as given in equation 22. The characteristic equation can be written as you see in equation 23, and radiant frequency is calculated as given in 24. Now we can see that in equation 24 that current tracking error and voltage tracking error parameters don't affect the oscillation frequency, and the condition of oscillation can be written as given in equation 25. This equation shows that in non-ideal case, the oscillation condition can still be controlled independently without interacting the oscillation frequency, and the effects of alpha 1, alpha 2, alpha 3, beta 1, beta 2, beta 3 parameters, it can be minimized by suitable pre-adjustment values of R1, R3, R5, and C5 components. And if we calculate the current transfer and voltage transfer functions in non-ideal case, we obtain the two equations given in 26 and 27. These two equations show that current tracking error and voltage tracking error parameters affect the gain, but not the phase difference between the quadrature outputs of current and voltage outputs. They affect only on the gain. Now let me give you the simulation results. We carried out two simulations for Biquad filter and also for third order.
Could you be more quick to finish your presentation, okay? Because
okay.
Time is in.
Okay. At the figure, you see the CMOS structure of multi-output second generation current conveyor, which we used in our study. And the MOSFET dimensions, which we used in the study, is located at the top table. And the passive components values are given in the bottom table. Here you see the width and length of the MOSFETs. We used the 0.18 micrometer parameters. And using these values, the center frequency is calculated as 1.59 megahertz, while in simulation it is measured to be as 1.57 megahertz in low-pass filter, and 1.55 megahertz in high-pass filter, and 1.58 megahertz in band-pass filter. The frequency domain responses of the filter are as seen in this figure. And now Here are the simulation results of the third order quadrature oscillator. In the simulation, for the simplicity, we adjusted the resistor values are all equal to 500 ohm, and C2 is 100 picofarad, C4 is 100 picofarad, and C5 is 50 picofarad. Using these values, the oscillation frequency is calculated as 3.18 megahertz, and in simulation, it's measured to be 3.24 megahertz by deviation of 1.88%, and the bias currents are adjusted to 50 microampere in two current conveyors in first two and 30 microampere in third current conveyor. Now you see the steady state waveform of the voltage outputs at the oscillation frequency of 3.24 megahertz. You see two quadrature outputs, and here is initial state waveform of the voltage outputs, and frequency spectrum figure is at the bottom. The most important feature of this proposed circuit is the electronic tunability. We set to a single control voltage, which is shown VC. It is the gate voltage of the all MOSFETs. We adjusted it in the range between 0.6 volt to 0.9 volt. And this figure shows the frequency variation by MOSFET gate voltage. It is adjusted between 2.12 megahertz and between 3.18 megahertz. And this figure shows the steady state waveforms of the current outputs. And amplitudes of current outputs vary between 170 microampere to 282 microampere. The control voltage variation was set to between 0.6 and 0.9 volt. If equal amplitude are needed, an additional automatic gain circuit can be used. In these two figures, you see the variation of voltage output amplitudes and current output amplitudes versus frequency. And these figures show the DHD results for both current mode and voltage mode operations. DHD values remain below 4% for current mode and below 5% for voltage current signals. However, these values can be significantly reduced by using automatic gain control circuit. And this figure shows the Lissajous pattern of the third order oscillator. This figure shows that there is 90-degree phase difference between the two output signals. From this pattern, the measured phase error between two output signals does not exceed 2.5% in the tested frequency range. And the phase error versus oscillation frequency remain below 2.5%. In this figure, you see the variation of the phase error. Now, the conclusions can be briefly as realization of a new electronically tunable MOS-C based third order quadrature oscillator and biquadratic filter, which are using all grounded passive components. Synthesis of voltage mode second order low pass, high pass, and band pass filters using second generation current conveyors, and current voltage mode third order quadrature oscillator using multi output second generation current conveyor from the proposed topology. Compatibility with integration through MOS-C implementation and using all grounded components. Low passive component sensitivity in both oscillator and filter circuits. Independent control of condition of oscillation and oscillation frequency. Electronic tuning of the oscillation frequency by MOSFET gate voltage both in voltage mode and current mode operations. Easy tunability via single control voltage by taking the resistor values equal. As we did in simulation, we used 500 ohms for all resistors. Quadrature phase error with less than 2.5% in an adjustable frequency band about of 1 MHz. THD below 4% for current outputs and 5% for voltage outputs. And the feature work, topology enhancement to achieve multi-phase oscillator with same advantage of the proposed work.
Okay.
Thank you for listening to me.
Thank you. Could you, if you compare your solution with similar solutions, could you point out the main advantage of your proposed design filter?
Yeah. In the literature, we searched and tested all the similar works, and in the article we put the comparison table. The most important advantage of this study is the circuit can produce both voltage mode and current mode outputs in quadrature mode, and also electronically tunable, and suitability for monolithic integration, and also for suitability for low voltage applications. And another remarkable feature of the circuit is the amplitude of the oscillator is comparatively higher than the similar works. We can say these features. For, yes.
Do you have the plan to make the real micro SIM using that design?
Yeah, we use 0.18 micron CMOS model parameters available for MOS-C.
Mm-hmm. Okay. Thank you.
Thank you for listening to me.
Mm-hmm. Thank you. So.
Hello, Chairman.
Hello.
I am Winai. So I have one question.
Hi, okay.
I am interested in the frequency tuning. Can your circuit tuning the frequency with the same condition? I mean, you can tune from the 1 kilohertz to 1 megahertz from the same condition. Hello, do you hear me? Can your circuit tune the frequency from 1 kilohertz to maybe to 1 megahertz with the same condition?
Can you answer? Hassan, can you answer or not?
Okay, thank you very much.
Okay. Because we are in a rush, so let's continue. And the next presentation will be from Denmark. Jakob Toft will present us the topic analysis of charge pump topologies for high voltage mobile microphone applications. Please.
Yes. Yes, hello, I'm Jakob from the Technical University of Denmark, and I'd like to present my work on analysis of charge pump topologies for high voltage mobile microphone applications. First, I would like to talk about the background for my project and the motivation behind it. Then I want to present the 6 charge pump topologies that are commonly used in the literature for high voltage gain charge pump implementations, and then talk about voltage scaling, dynamic power losses, and settling time of these topologies, and wrap up with a conclusion. So MEMS microphones are used widely in smartphones, laptops, smart assistants, etc. And there is a demand for a higher signal to noise ratio from MEMS microphones to improve the performance of stuff like smart assistants, Google Home, Alexa, Siri. And then capacitive sensing microphones, the SNR is given by the sensitivity over the noise. And sensitivity is a function of the bias voltage divided by the air gap times the change in air gap per change in pressure. So using a higher bias voltage increases the sensitivity, which increases the signal to noise ratio. So MEMS manufacturer has created a new MEMS structure that requires 180 volts of bias voltage, which this must be generated from a supply of 5 volts, and the power consumption should be less than 20 microwatts, and the area should be limited to 1/4 of a square millimeter to fit inside the small microphone packages. So the goal of this work was to determine which charge pump topology is optimal to solve this problem. The generic operation of charge pumps is that you have a floating capacitor and switches that connect the bottom and top plate of the capacitor to different voltages. For example, here in phase 1, the capacitor is charged by V1, and then in phase 2, the capacitor is lifted by V2 to a resulting output voltage of V1 plus V2. And when you cascade multiple capacitors, they can be configured in multiple ways. Which is the basis of different topologies. There are 6 general charge pump topologies used in literature, where 3 of them is the Dixon, the Pelliconi, and Cockcroft-Walton topologies. And difference can be noted here that the Dixon has the capacitors in parallel, whereas the Cockcroft-Walton is stacking capacitors. The 3 other topologies are the Fibonacci, the Doppler, and the heap topology. And the ideal voltage gain of these 6 topologies are given by this table, where the Dixon, Pelliconi, heap, and Cockcroft-Walton topologies have a linear voltage gain of n plus 1, where n is the number of stages. So a 9-stage charge pump using these topologies would have a voltage gain of 10 volts per volt. The Fibonacci voltage gain follows the Fibonacci number series 2, 3, 5, 8. And so forth, and the Doppler topology doubles the voltage in each stage, so 2, 4, 8, 16, 32. However, in reality, it's not possible to achieve the ideal voltage gain because parasitic capacitances reduce the voltage gain in every stage of a charge pump. From the early example of a generic topology, I've introduced a parasitic capacitance to the top plate of the flying capacitor C pump. And in phase 2, when the capacitor is lifted by V2, the parasitic capacitance is still referenced to ground. So a charge sharing occurs between the 2 capacitors. And the voltage gain is output voltage is now given by V1 plus V2 times C pump over C pump plus C par parasitic. This can also be represented by saying that alpha is equal to C pump over C pump plus C par, and then the resulting output voltage of the topologies changes, where the Dixon and Pelliconi topologies share the same equation of the voltage of the previous stage plus the supply voltage times alpha. The heap topology has voltage gain of the supply voltage plus the voltage of the previous stage times alpha. And the Cockcroft-Walton, Fibonacci, and Doppler topologies all depend only on the voltages of the previous stages. The alpha in some topologies depend on the topology because capacitors are stacked, and when you stack a capacitor, the effective capacitance is reduced. In the heap topology, you charge all the capacitors in parallel, and when you connect them in series, the effective pumping capacitance is reduced. So the parasitic capacitance has a larger impact on the voltage gain. So I use these equations to calculate the voltage gain of area-limited implementations, where I used device parameters extracted from a process design kit of a 180 nanometer SOI process for high voltage electronics. Device parameters like capacitance density of capacitors, parasitic capacitance on source, drain, and gate of transistors, and of anode and cathode of diodes. And then I used devices with the correct voltage rating to implement these different topologies. And as it can be observed, the Fibonacci and Doppler topologies still exhibit a exponential voltage gain and can with less than 10 stages and a restriction of 1/4 square millimeter reach voltage gains of more than 36 volts per volt, which is required to boost 5 volts to 180 volts. The Dixon and Pelliconi topologies have a linear trend, as seen in the previous table. But the voltage gain of the Cockcroft-Walton and the heap topologies is diminishing and cannot boost the 5 volt voltage to more than up to the required 180 volts. So these two topologies, heap and Cockcroft-Walton, are not suitable for the application. In addition to calculating the voltage gain of a quarter square millimeter area, also calculated it for a smaller area to reduce the size of the implementation and see if it was possible. And the Fibonacci and Doppler still have the exponential voltage gain and they can deliver sufficient voltage gain. And the Dixon and Pelliconi are also capable of achieving a suitable voltage gain, although the Dixon now requires 41 stages to provide 180 volts at the output. So to further reduce the amount of topologies to consider, I decided to investigate the dynamic power losses based on parasitic capacitances, as the output power of the converter will be very low because the MEMS is a capacitive load, have a low leakage current. So I figured that most of the power losses would come from switching of parasitic capacitances. And the power loss is given by the switching frequency times the parasitic capacitance times the voltage swing squared. And I based my power loss calculations on the 0.04 square millimeter implementations because they're smaller, so they have less parasitic capacitance, which is beneficial in terms of reducing the dynamic power losses. The voltage swings in the topologies are dependent on the topology. The Doppler topology in the last stage has a voltage swing of 90 volts in 2 nodes, A and B, whereas the Fibonacci topology only has voltage swings of 69 volts. And the Dixon and Pelliconi topologies only have voltage swings of 5 volts across the entire charge pump implementation. Because the dynamic loss scales with the squared voltage swing, the Pelliconi and Dixon were expected to perform better. So for the Dixon and Pelliconi topologies, I extracted the parasitic capacitance of the entire charge pump, all 41 stages for the Dixon, and all 36 stages for the Pelliconi, for a combined parasitic capacitance of 4 and 4.2 picofarads. And for the Fibonacci and Doppler topologies, I only extracted the parasitics for the high voltage swing nodes. And for different voltage swings, the 5 volt, 69, 90 volts, the Dixon and Pelliconi only consume or lose about 10.5 microwatts to switching of parasitic capacitances, where the Fibonacci and Doppler topologies lose 4 to 7 times more, 43 and 73 microwatts. So even though the Fibonacci and Doppler topologies were only evaluated in 2 nodes of the entire charge pump, they use more power than allowed by the MAPS microphone application. So these topologies were also out of consideration for a final implementation due to power losses. Then I decided to look into the settling time, as a fast startup time is beneficial in a smartphone, for example, so you don't have to wait before you start talking. Where I used a switch capacitor converter model, which can be used to model a charge pump, as charge pumps are switched capacitor converters. The model consists of a transformer that represent the voltage gain, the unloaded voltage gain of the charge pump, and an equivalent output resistance, and a load resistance that models the load. For the case of the MAPS microphone, the load resistance is replaced by a capacitor of approximately 10 picofarads, which gives a time constant for an RC circuit of R times C load. And the output resistance is a root sum square of ISSL and IFSL, where ISSL is a resistive component representing the slow switching limit of a switch capacitor converter. And ISSL is inversely proportional to the size of the capacitors and switching frequency. So switching it faster and using larger capacitors reduces ISSL. And the IFSL represent how much the on resistance of switches used in the switch capacitor converter impact the output resistance. So using larger transistors with a lower on resistance will lower IFSL. The on resistance of the Dixon and the Pelicone is different because the Pelicone is implemented using transistors, whereas an inherent level shifter function in the topology. So there will always be a high gate to source voltage, whereas the Dixon topology has a larger voltage stress across devices of 10 volts, which is more than any of the gate source voltage ratings in the process allow. So it has to be implemented using 10 volt diodes. Based on this, I calculated the equivalent output resistance, where in the first iteration just assumed that diodes had the same on resistance as minimum size NMOS transistors. And PMOS transistors extracts have a 37 kilo ohm on resistance. Based on this, the Dixon was evaluated to have an equivalent output resistance of 2.4 gigaohms, and the Pelicone an equivalent output resistance of 1.6 gigaohms. And given the equivalent output resistance, the settling time, 95% settling time, could be calculated, where the Dixon would have a 73 millisecond settling time and the Pelicone 49. So in terms of settling time, the Pelicone topology is performing better than the Dixon. In addition to that, when the charge pump settles near the final voltage, the voltage drop across the diodes would drop further, and at voltage drop of only 0.4 volts across diodes, the on resistance would be 12.7 gigaohms, which would increase the R out significantly and lead to a voltage drop. So more stages would be required to compensate for the low output voltage, which would further increase the output resistance. Alternatively, high voltage transistors and level shifting bootstrapping circuits could be used, but this would increase the parasitic capacitance in each stage of the Dixon implementation, which would require more stages to implement the charge pump that could reach the sufficient voltage gain, and more stages would increase the R as well. So in terms of settling time, the Pelicone performs better than the Dixon, even if measures where you avoid use of diodes could be implemented. So in conclusion, 6 charge pump topologies were analyzed for a MEMS microphone application, where the target was to boost 5 volts to 180 volts. And the implementation was limited to a power consumption of 20 microwatts and an area of 0.25 square millimeters. The Heap and Cockcroft-Walton topologies did not scale well when parasitic capacitances were considered. The voltage gain did not scale well. And the Fibonacci and Doppler topologies consume too much power due to large voltage swings. And the Dixon topology has a long settling time compared to the Pelicone topology due to the use of diodes, which is an effect of the large voltage stresses in the topology. So based on the analysis, the Pelicone topology appeared to be the optimal topology to boost 5 volts to 180 volts for the MEMS microphone application, based on the used 180 nanometer SOI process. Thank you.
Okay.
Any questions?
Okay, thank you. So any questions from audience? I don't see any questions. So I would like to ask how these restrictions for area for power consumption were set?
The area is restricted because MEMS microphones are quite small. The footprint of an entire MEMS microphone is usually 2 by 3 millimeters, and that's the outer dimensions. And the inside there's maybe 2 by 1, and half of that is usually used for the MEMS structure. So there's 1 square millimeter for the ASIC that accompany the MEMS structure, and of that ASIC you also need to fit the digital logic and a signal chain. And charge pumps are usually restricted to use no more than 1/4 of that. And in terms of power, there's also power budgets because mobile applications, they want low power consumption. So the lower the power consumption your charge pump can have, the more power you can use in your signal chain to improve the signal to noise ratio of your amplifier and digital to analog converter. So the objective was in some sense to minimize the area and the power consumption of the charge pump.
Okay, I see. So any questions? No questions. So thank you, Jakub.
Yep.
And we have 15 minutes left to the next session, so we should rush. And our next presenter is from Serbia, Damian Rankovic, and he will make presentation Argus CNN accelerator based on kernel clustering and resource-aware pruning. So Damian, I ask you to be short as possible, okay? Because we need to close our session till 15:30.
Yes, sure. Do you see my screen?
Yes.
Okay, thank you.
So,
we wanted to optimize accelerator and pruning methods for the convolutional neural network, mainly to implement it on edge-based devices like small FPGAs. So overview of the presentation. First, we will see just how some basic processing of convolutional layers. Then we will talk about the proposed pruning algorithm for the convolutional neural networks, ideas, benefits, and benchmark. And then we will see briefly the hardware accelerator architecture called Argus with some benchmarks and our architecture of top level, and the main part is convolutional core. So just as a short introduction to 2D convolution, the convolution is done on the input feature map, which is in first layer also of convolutional network. It's just the image, and this can be image in RGB format. And we are convolving this image with kernels, many of them. So what we are actually doing is dot product between, for example, this blue part of the input feature map with the kernel, and that dot product result in one output feature map. So this is rather computationally very expensive, because there are many layers and many kernels. So some of the networks like VGG16 uses about 15 billion MEC multiply accumulate operations to classify just one image. Of course, there are some more compact today, but this is some extreme example. One way to tackle this complexity is to create good and powerful hardware, but another way can be done using the pruning of CNN. So basically, the pruning in majority of pruning algorithm is done on each kernel differently or filter. So here is the example on the left side how the kernels are pruned. So these gray parameters of kernel are left after pruning, and other ones are zero. So the idea of when we are creating the accelerator is to skip all calculations where we will have zero as a result. So multiplication with zero is zero. So we need to skip all this white stuff. If we are creating the accelerator in regular way, then we need one module which will do this skipping of zeros per each kernel. So this is rather expensive, especially on the FPGAs to be efficient. So we propose to group similar kernels inside the cluster and to prune them in same way. So we can use only one zero skipping logic per whole cluster. As you can see on picture here, all kernels in cluster are pruned in the same way. Another idea was taken from the previously published work. So let's imagine that this is kernel with 3 × 3 × 64 size. So each of these, we call this stick, can be divided into 8 groups of 8 weights, so 64 in total. The idea of original work is to eliminate 4 parameters or weights from this kernels inside each group of 8 weights. In this case, we will have same computational cost on each of this group, which will balance workload among the processing elements. What we improve here is the analysis on usage of this algorithm on the FPGA. So originally, the zeros, the non-zero values, 4 non-zero values could be on this, and this position, which means 5 different options. This will actually use 5-to-1 multiplexer, which is expensive on the FPGA, which mainly has 6 input LUT, which is suitable for 4-to-1 multiplexer. So we further constrain this pruning algorithm like this picture. And finally, we combine previous and this one into one pruning algorithm. So we are pruning each group of 8 weights like this, and we are using the clustering to find the most similar kernels to prune them in the same way. In total, this idea saves about two times the used resources on FPGA. And the first idea, if cluster is, for example, 2, we will save two times in terms of zero skipping logic. We did pruning on MobileNet, ResNet 50, and VGG because these are 3 different CNNs. And here are the results. These are the results of unpruned network, and these are accuracies, top 5 accuracy after pruning. So we can see that this is that we have small loss, but the loss is pretty much very small, and the application on which we did pruning on ImageNet is a rather hard task for edge-based computing. Here is the top level of this configurable accelerator. Mainly it has 2 cores. It has convolutional core and the dense layer processing core, which is used for other layers. This processing of other layers is not that important in terms of time, so we will see more detailed explanation of this convolutional core. Beside the convolutional core, there are some data move engines which are connected directly to the DRAM through XI full interfaces. The number of convolutional cores and DLP cores is configurable, so we can choose based on the complexity of the process network. Here is the convolutional core in more details. There is register file for the configuration. There is a DRAM arbiter. There is also input stream, which is actually used as a cache buffer. There is a link. A link is used for stacking more convolutional cores, and the main part of this convolutional core is processing element array. Processing element array contains FSM for controlling. It has the memory bank that stores weights and non-zero indexes. It has input feature map point selectors, which are actually zero skipped logic, and inside these there are actually 4-to-1 multiplexers. There are 32 processing elements, which has 2 DSPs on, and they are clocked at 500 megahertz on the FPGA. And at the end, there is a result collector, which collects results in round-robin manner from these processing elements and does the rounding and the activation function on these results. Here are some benchmarks to the sum with the sum of the previously published work. As you can see, frame rates on the AlexNet for convolutional part only is comparable to the other. and better than some. Compare full network is better than just the NVIDIA solution, but this is due to the very big fully connected layers at the outputs, which are currently, let's say, obsolete. On the other hand, we have a very favorable comparison with using VGG16. In terms of performance, the core has the best among these presented here. And what is actually the power of this core is the utilization of hardware. So if compared to the other FPGA solutions, we can see that Argus uses at least twice time less LUTs, and one of the smallest number of the MAC units, which are actually the DSP blocks. So the whole benefits of the core is possibility to be fitted inside the edge and small, let's say, small FPGA devices, and to have comparable performance with the others. In terms of mobile net, we can see that we have a little bit lower performance in terms of frames per second compared to the accelerator that is optimized especially for the depth-wise convolutions. But on the other hand, we can see that this solution, which is better in terms of frame rate, has almost has more than 10 times more DSP blocks inside the accelerator. So this cannot be fitted on the edge-based computing. And here is another benchmark. You can find these references in the work. We did a comparison in terms of giga operation per second per use DSP, per use LUT, and per use BRAM. As can be seen, the Argus has the best density among these accelerators in terms of giga operation per DSP. It's not the best in terms of giga operation per LUT, but it's not that big difference. And in terms of giga operation per use BRAM, on the FPGA device, it has at least twice better performance density. At the end, I would like to conclude what is done in this work. So we proposed the novel CNN pruning algorithm, introduce the kernel clustering, which will reduce the zero skipping logic utilization by factor of 2. We enhance the previously published pruning algorithm, and we tailor it especially for the FPGAs. And at the end, we proposed the architecture called Argus. This is complete CNN hardware accelerator, which is able to prune to process the dense and sparse CNNs pruned by these algorithms. And we can see that it has a balanced utilization of available resources on modern FPGAs. So it enables usage of this of Argus on the cost-effective FPGA devices.
Thank you. So questions? I will ask one question. For what kind of application your accelerator is designed to be used?
Yes, actually, this can be used in industry. What I saw is that some kind of similar accelerators are used to classify fruits, to classify damage bottles and stuff like that. Yes, in industry mainly for today.
For image processing, yeah?
Yes, yes, sure, sure.
Okay, thank you.
Thank you.
So if we don't have more questions, let me finish the session. We exceeded our time exactly half an hour, and now it's time for next session on power electronics. And thank you for participants, for all audience, and good luck.